Hello everyone, my name is Will Stonebridge, and today I'll be going over a simplified approach to Q learning, which was originally proposed by Wang et al. Particularly in the field of robotics, a common problem is making a machine move efficiently. There's not really an algorithm for that, so reinforcement learning is usually used to solve this problem. A common subset of reinforcement learning is Q learning, where basically you have two networks, the actor, which learns how to walk, and then the critic, which has to learn a function that looks at states, actions, rewards, and the next state, and it says, hey, you took this action in this state which resulted in another state. How is that going to affect the reward in the long term, not just instantaneously? I'm going to quickly go over one of the baselines used in Wang et al.'s paper. This is the TD3 algorithm, and it serves as a good example of how actor-critic algorithms generally work. You start by initializing your networks. That's a critic and agent network. You also initialize a replay buffer, which is used to store interactions that will be trained on later. These replay buffers, especially in this algorithm, are very complicated. Within the training loop, you have the agent interact with the environment, and you store those interactions in the buffer. In order to train the Q network, you want to minimize the mean squared Bellman error, and the agent just seeks to maximize the output of the Q network. Let's take a closer look at the actions that are output by the agent network. In this case, we're looking at a cheetah, and the action is just a list of torques that are pushed on the cheetah's joints. A common issue is these values explode after the first few steps of training because it sees that by creating a very large action, it can move itself forward. However, this is undesirable because we want the agent to explore. We want it to look at maybe more mild actions. For my paper, I chose to re-implement the Streamlined off-policy algorithm, which was introduced by Wang et al. Now, it makes a lot of minor changes to TD3 and also soft actor critic. However, the two most important ones are as follows. It introduces G-normalization, which basically looks at the absolute value of every action component, sums them up, and then divides them by the action dimensionality. If this is greater than 1, then it divides it by the previously mentioned value. This basically ensures that the average magnitude of the agent is never greater than 1, effectively normalizing the output. The second thing it introduces is the emphasizing recent experience buffer. This is a significant change from the previously mentioned priority experience replay buffer in that it's a lot simpler than its precursor, and it also works on a different concept. Basically, instead of looking at the uniqueness of interactions, it slowly samples more and more recent interactions throughout training, and this is proven to achieve state-of-the-art results. The first experiment I conducted was an ablation study of G-normalization. The first two charts show the agent output without G-normalization. As you can see, it's huge, and the corresponding action. Basically, the only actions are the maximum and minimum output. However, when you add normalization, you can see that you get much more reasonable magnitudes, and the corresponding actions of those outputs are very well exploring the action space. From an overall performance perspective, my agents perform pretty well. As you can see, they move generally pretty quickly. The human struggles a bit. However, overall, I'm able to achieve a cumulative reward that is comparative within 10 to 15% of the original algorithm. Without the ERE buffer, my agent actually performs pretty well too. As you can see, the cheetah is moving pretty fast, and the maximum reward is about the same as the original paper, which is below. Lastly, I trained my algorithm on two environments that were not evaluated in the original paper. The first is Reacher, which basically just has a hand that tries to get to a red dot that spawns randomly within the environment. As you can see, it does this pretty well. The second and much more difficult environment is human stand-up, which is basically just the human again. However, you have to teach it to stand up, and then it walks. I think G-normalization actually works against us here, because in order to stand up, a very large movement on multiple joints is required, which is exactly what G-normalization seeks to prevent. To summarize, the SOP algorithm introduces simple but effective solutions to two major issues with actor-critic algorithms, while still maintaining state-of-the-art results. G-normalization avoids the issue of exploding agent outputs by ensuring the magnitude of the output is always 1, and ERE buffers are able to match the performance of priority experience replay buffers with significant less complexity, but maintaining those state-of-the-art results.